Hi everybody, this video is on section 4.8. It's called row space and column space. So first we begin with a definition. Let A be an m by n matrix. Okay, you could also write it this way. Remember, A is inside the set of m by n matrices with real coefficients, right? That means the same thing, okay? What is the row space of the matrix? The row space of the matrix. So the row space of A is the subspace of Rn spanned by the row vectors of A. And this is denoted, you just write it in one word like this, row space A. Okay. Row space A. The column space of A is the subspace, this time of Rm, spanned by the column vectors of A. And this one we denote like this, COL space, so call space. That's how we write it. Okay, so we write this one like this, we write this one like this, okay? So let's do a quick example here so that you understand what I mean when I say that the row space is a subspace of Rn and the column space is a subspace of Rm. So let's do an example here. Let A be the following matrix: -1, 9, 3, -7. Okay, so what is the row space of A? So the row space of A is going to be the span of the row vectors. So take the rows and turn them into vectors. So it's going to be the span of those two row vectors. Okay. You'll notice, by the way, that this is a subspace of R3. It's a subspace of R3 because these are vectors with three components, right? There are three things. And of course, that does correspond to, this is a 2 by 3 matrix, right? M by N. And so for this first guy, we're talking about this, right? Subspace of Rn. Now, what would the column space be? The column space is going to be the span of the column vectors that you see. So 2, 5, -1, 9, and 3, -7. And you can see right here that this is a subspace of R2, right? Because these are two-dimensional. And so just to point it out in case you haven't already noticed, of course, M is what appears here, right? But you don't have to memorize that. Just look at how big the columns are. Look at how many vectors are in there or how many components are in the columns, and then that'll tell you what it's a subspace of, okay? So this arises, we can ask a natural question here. So question. Do the row, and we can ask the same question with column, so I'll put it in parentheses above it. Do the row vectors of A form a basis for, I mean, we know they span. The question is, do they form a basis for the row space of A, or if we're using columns, do they form a basis for the column space of A? So you should hopefully understand that this is not necessarily the case, right? I mean, look at this last example. We had the span of 3 vectors, right? 3 vectors, but we know you only need 2 vectors to span R2. So there's no way that those 3 vectors could form a basis, right? R2 has dimension 2. So the answer, of course, to this question is not necessarily. I mean, you might get lucky, but not necessarily. They span, but are not linearly independent in general. Okay. So there is a nice way to figure out a basis for the row space or the column space of a matrix. And so that's what the next theorem allows us to bring to the table here. So if A is row equivalent to B, row space A is equal to row space B. This is a really nice result, okay? This is saying that if you use elementary row operations on a matrix, you do not change the row space of the matrix. So this leads us to the next theorem. This theorem says the set of non-zero vectors in any row echelon form of a matrix A forms a basis for row space of A. Okay. So what this means is when you get your row echelon form here, whatever it is, all the ones that are non-zero, these become your basis, okay? So if you call this first row vector v1, the second row vector v2, and vector v3 or whatever it is, it doesn't have to be 3 of them, then a basis for the row space of A is equal to v1, v2, v3, right? Okay, so we already have a name for that though. The number of non-zero rows in a matrix, after you do the row echelon form, we have a name. That's called the rank of the matrix. But we also know that that's going to equal the number of things in the basis, right? So if we look at this guy, the rank of this matrix, if we call it A, the rank of A is 3, but then that's also equal to the dimension of the row space. Because remember, dimension just means how many vectors are in the basis. And so this gives us a fact. This is always true. So I'll just write this as fact here. The rank of A is always equal to the dimension of the row space of A. Really nice fact here. Okay, so let's go ahead and do an example. Determine a basis for row space of A if A is equal to the following matrix. 1, -2, -2, 1, 4, -7, -6, 5, -1, 5, 8, 2, 2, -5, -6, 1, 3, -6, -6, 3, 5, -9, -8, 6. Big matrix, right? Okay, so we're not going to sit and do, I'm not going to show you every single step, but you just put this matrix in row echelon form, right? You guys are already comfortable with that. So after you do your row operations, you'll end up with 1, 0, 0, 0, 4, 1, 0, 0, -1, 3, 0, 0, 2, -1, 0, 0, 3, 0, 0, 0, and 5, 1, 0, 0. Okay. Notice that you only have 2 non-zero rows, right? This guy and this guy are your only 2 non-zero rows. And so we're ready to write. This means that the basis for row space of A is equal to these two vectors, 1, 4, -1, 2, 3, 5, and 0, 1, 3, -1, 0, 1. What is this a subspace of? This is a subspace of R, let me see, 1, 2, 3, 4, 5, 6 of R6. So it's a two-dimensional subspace of R6. And notice also that the dimension of the row space of A, the problem didn't ask us for this, but we can write this down. The dimension of the row space of A, of course, is 2, right? Because there are only 2 vectors in the basis. Now, there is something nice to notice here. This gives us a straightforward technique for finding the basis or a basis for the span of any set of vectors. What do? First, create a matrix A using the vectors as rows. Then put A in row echelon form using elementary row operations. And then the basis is equal to the set of non-zero rows, non-zero row vectors. Okay? Pretty cool, right? This gives us a nice technique that we could have even used in earlier sections when we were figuring out what this, where we were trying to find a basis for the span of a set of vectors. So let's quickly do another example here. Find a basis for the subspace of R4 spanned by the following vectors: 1, 2, 3, 4, 4, 5, 6, 7, and 7, 8, 9, 10. So we've got 3 vectors, and we want to find a basis for the subspace spanned by those 3 vectors. So what do? So create a matrix A, and we're going to put those vectors as rows. First row will be the first vector, second row will be the second vector, third row will be the third vector, okay? And then, of course, use your row operations. I'm not going to show you all the steps here for the sake of time, but we end up with 1, 2, 3, 4, 0, 1, 2, 3, and then 0, 0, 0, 0. And again, look at the non-zero rows here. Those are the ones that are going to give us a basis. So the basis for span of S is equal to 1, 2, 3, 4, and the vector 0, 1, 2, 3. Now, we haven't talked about column space, but here's the really nice thing. Surprisingly, we do not need column operations. To determine a basis for the column space of A. So we have a nice theorem that explains how we can find the column space using a very similar method to what we just did, okay? There's going to be one little difference. So theorem. So suppose we have an M by N matrix A. the set of column vectors of A corresponding. That's such an important word that I'm going to underline it, okay? The set of vectors or column vectors of A corresponding to those column vectors containing leading ones in any row echelon form of A is a basis for the column space of A. So this is important. Corresponding, in other words, you're still going to look at the column vectors of A. And that's how you figure out the basis for the column space. So you do your row operations, but you're still going to need to go back and look at the original matrix to write down your answer. Okay. So let me quickly do an example here to demonstrate this. Determine a basis for column space of A if A is equal to 1, 2, 5, negative 3, 2, 4, 10, negative 6, negative 1, negative 2, negative 5, 3, negative 2, negative 3, negative 3, 2, negative 1, negative 1, negative 1, 1. Okay. So the idea is, remember, we're looking at these as individual columns here, okay? And we want to figure out how we can form a basis for the column space of A. So we're going to do elementary row operations here. And so if you do your row operations, just put it in row echelon form like normally, okay? So we have a 1, a 2, or sorry, let me write it this way. 1, 0, 0, 0, 2, 0, 0, 0, negative 1, 0, 0, 0, negative 2, 1, 0, 0, negative 1, 1, 1, 0. Now, let's read the theorem carefully so you guys understand what to do here, okay? We want column vectors of A that correspond to column vectors containing leading ones in the row echelon form. So let's circle the leading ones here. Our leading ones are here, here, and here, right? So what you do is you look at the columns that contain those. We have this column, and this column. So that's column 1, 4, and 5. And what we do then is we don't use those columns, but we use the columns 1, 4, and 5 in the original 1, 4, and 5. So these are the ones that form a basis. So those 3 column vectors. And so this is how we write our answer. A basis for the column space of A is going to equal 1, 2, 5, negative 3, negative 2, negative 3, negative 3, 2, and negative 1, negative 1, negative 1, 1, right? And of course, this is a subspace of R4. So this is a subspace Okay, which this is all very nice. The reason why we like this better than doing column operations is so that all you have to do now is put something in row echelon form and you can find a basis for both the column space and the row space. You don't have to do two computations. So this means putting a matrix in row echelon form gives you both of these for free. Now you may have noticed something, right? If we were doing row space for this last example, we would have also had 3 vectors in the row space. So that would have given us the row space, right? So we had 3 vectors in the row space and 3 vectors in the column space. So that means the dimensions of the row space and the column space are equal. This is actually always true. So we notice the fact the dimension of the row space of A is equal to the dimension of the column space of A. Now be careful, just because the dimensions are equal, it does not mean the vector spaces themselves are equal. So let me just say this is always true, but be careful. They are not equal subspaces in general. They can't be equal subspaces because, of course, they're each subspaces of different vector spaces, right? We know that row space of A, remember we talked about this earlier, right? Row space of A is a subspace of Rn. And column space of A is a subspace of Rm. In other words, because they live in different dimensional spaces, they're not exactly equal to each other, right? So it's sort of like saying if they were both two-dimensional subspaces, they're both planes. They both can be thought of as planes, but one is a plane that lives in a higher dimension and the other is just a plane that lives in a lower dimension. So they're both planes, but they're not quite the same. Okay, so these are not quite equal, obviously, because these guys may be different. So even though these guys are the same dimension, they live inside of different spaces, so they're not exactly equal subspaces. Same dimension, but not equal subspaces. All right, everybody, that's it for this video. Thank you so much for watching.